Hello everyone, today's name reaction is Peterson Olefination. So what is Peterson Olefination? Here as you can see, we have taken two diastereomers of beta hydroxysilane. Now why I am calling it beta hydroxysilane? Because with respect to this SiMe3, there is hydroxy, that is OH, at the beta position. So that is why the name is beta hydroxysilane. We have taken two different diastereomers. Now here we are focusing on the groups SiMe3, or there may be any other R group instead of methyl, but focus is on this SiR3 group and OH. And these two side there may be any group. Now these two groups I have presented here as R and R prime, but this may be same also or it may be different also. But important point is we have taken two different diastereomers, right? Now when we are having two different conditions, suppose you have taken only one particular diastereomer, you have taken the first one and you are treating it under acidic condition, it may be Lewis acid or Bronsted acid, or base such as potassium hydroxide, like potassium hydride, this type of base. When we are using, we are getting two different types of alkenes. One is E alkene, another one is Z alkene. Now why I have written major here? Because when it is acidic condition, this alkene will be the major, and when it is basic, the Z alkene will be the major. Now the same type of reaction condition, that is one is acidic condition, another one is basic condition. If you apply for the second diastereomer, now the interesting point is it is becoming reverse, it is giving us the reverse result, right? Now if you particularly focus on one condition, suppose I am focusing on the acidic condition, keeping the condition same, when you check the result for the final product from two different diastereomer, so I am fixing the condition acidic. Now see, from the first diastereomer you are getting E alkene as the major, but in the second case you are getting the Z alkene as the major. And you can also change the acidic condition. Now you can focus on the second condition also. So under the same condition, that is the basic condition, again they are giving different result. Now this is very important features of this Peterson Olefination. This is basically the elimination step, right? Where SiMe3 group and OH group, these two are removed, and in this place we are getting a new CC double bond. So we can say this is stereospecific elimination, because when you are fixing the condition to acid or to base from two different diastereomers, you are getting two different alkene, right? E alkene or Z alkene. Now next we will see the mechanism. Now I have chosen the first diastereomer. From the previous slide, two diastereomers were there, but I have chosen the first one. So here you can see SiMe3 and OH group, they are opposite to each other. Now the same molecule I can draw in this way. So there is equivalent sign, you can understand, it's the same molecule. Now we will see under two different conditions what is happening, why we are getting different type of alkene, Z and E. So when it is acidic medium, suppose H2SO4 or some Lewis acid we have taken. Now again equivalent sign. So the same molecule I have drawn in a different way. But why I have done so? See, this part I have not changed, but I have changed it slightly. So what I am trying to do, first when I have converted to this second, I have kept everything same, because here hydrogen is above. So when you are looking from this side, this will be the same picture, right? But suppose another equivalent sign, why I have done so? Because my purpose is to bring these two groups anti to each other. And in doing so, why I am doing so? Because when it is in acidic medium, in presence of H+, this OH will be converted to a OH2. Now this is a very good leaving group, right? So when this is a very good leaving group and in the medium there is water present, so this can attack this SiMe3, this bond will be broken, there will be a new CC bond, and this OH2 will be removed. So this is anti-periplanar transition state. So to make this anti-periplanar transition state, I have to change this the positions of R prime, OH, SiMe3, everything. Okay. So this is the anti-periplanar transition state by which we are getting the E alkene. These two groups are opposite to each other. Now when it is basic condition, the same molecule, now what I have done, I have again the equivalent sign. Now I have brought these two groups in the same site, and there is a purpose behind it. So under basic condition, suppose we have taken potassium hydride, this H will be removed and there will be negative charge generation. Now this negative charge, it can make this type of, it can attack this SiMe3. So there will be, this bond will be broken, this will be broken, and oxygen silicon bond, this is very stable bond, this will be the byproduct. So ultimately these two bonds will be broken and we will get CC double bond in this position. So this is syn periplanar transition state. So two different type of transition state for acidic medium and basic medium, and that is why we are getting different result. So here both groups are on the same side. So this is Z and this is E. Now you can do the same thing. I will also suggest you to do the mechanism for the other diastereomer, so that you can, by following the same mechanism, so that you can understand that for the other diastereomer, acidic medium and basic medium will give you the reverse result. Okay, so please do that. So this is the attractive feature. A single diastereomer of beta hydroxysilane, it can be the precursor for the preparation of both E and Z. So depending on our requirement, we can choose the acidic condition or basic condition. But there is a disadvantage, or you can say that, I will not say disadvantage, but I am trying to say is that we must have the availability of just one diastereomer, because if you are having mixture of diastereomer, when you have made this molecule, suppose starting from some other starting material, and you have the mixture, then from the mixture you cannot do this elimination. So you have to have the pure diastereomer, only one diastereomer in pure form. So it requires the availability of just one diastereomer. If you have mixture, you have to first separate and then only you can proceed for the elimination step. So that is the reason availability is very important. Now how we can make beta hydroxysilane? So beta hydroxysilane you have already seen in the previous slides. There are two diastereomers, but how we can make it? Now Peterson reaction we can say that will be most useful when we can make beta hydroxysilane in stereoselective manner, and that you can do only in certain cases. It is not that always you can do so by just any method. If you want to make it stereoselective, that is beta hydroxysilane, the diastereomeric mixture that you are getting, among this one of the diastereomer will be major, then it is stereoselective. But that is the challenge. But Peterson, because if one of these is major, then you can focus on that particular beta hydroxysilane, that is a major one. Then only we can get from, because if there is a mixture, suppose 50-50 mixture, then there will be, we have to do the separation. But if one of these is major, then it will be most useful, because if it is stereoselective formation of beta hydroxysilane, we can avoid the separation step of the diastereomeric mixture, and that we will call as direct Peterson olefination or one-pot Peterson olefination. That will be useful. So we will see some methods where stereoselective formation is possible. We will also see some methods where it may not be stereoselective. Both we will see. So here you can see this example, CRAM type Felkin-Ann type addition of a nucleophile. What is the nucleophile? Nucleophile is Me minus, methyl minus, to the alpha silyl ketone. So first there is a formation of alpha silyl ketone, and how we are getting it? If you look at the first product, here we have SiAb2PH. It can be, that is in general you can write it as SiR3, where R may be any groups. Now in presence of Mg there will be formation of Grignard, that is MgCl, and then C4H9COCl. So there will be a negative charge after MgCl formation. This negative charge, it will attack this COCl. Cl will be removed. You will be getting this alpha silyl ketone. And in this alpha silyl ketone, if this Me, it is attacking at this position, and that will be CRAM type addition. So only one of the diastereomer you will get it as a major product. So this example is taken from Carruthers. I will mention the books in the description box along with the page number, so you can check it. So here one of stereoselective formation is possible because it is CRAM type addition. Then epoxidation of an alkynyl silane. So this is our alkynyl silane, as you can see, where both these SiMe3 or SiR3 any group and the other alkyl group, they are on the same side. You can also take the reverse one. Suppose you have taken Me3Si double bond, then there is some R group. That is another possibility. In presence of metachloroperbenzoic acid, we are getting epoxidation where these two groups are on the same side. And finally, in presence of some copper lithium, in general I can write it like this. So ultimately, we are getting this compound. So here what is happening, this C3H7, which is the R group, this will attack at this position. Okay, so if this is attacking here, then this bond will be broken, and there will be for this side we will get OH, and the other side we will get a new bond which is C3H7. So this is stereo-specific formation of this beta hydroxysilane. Why I am saying so? Because if you are starting from this trans, that is the other isomer for the starting material, you will get the other final product, that will be the other diastereomer. So in this case, the nucleophile, that is R minus, it is SN2 type of mechanism. This is taken from Carruthers, but same type of example is also mentioned in Clayden. I will also give the page number. You can check it in the description box. So this is SN2 type reaction, because if it is not SN2, suppose if it is SN1, then the attack is expected from the other side, where beta silyl cation will be very stable, but that is not happening here. It is SN2 and it is stereo specific. So this is also another way where you can make a particular diastereomer of beta hydroxysilane. Next example is dihydroxylation of an allyl silane. So this is an allyl silane. If you focus on this part, this is allyl silane, and in presence of the reagent for dihydroxylation, which is from the same side, you can get this 2 OH group at the position of CC double bond, and this is also beta hydroxysilane, right? This example is also from Carruthers. Now the next reaction, you can do, that is the general way I have written this reaction, reduction of alpha silyl ketone. So this is our alpha silyl ketone, or you can call it beta ketosilane. Both are actually the same molecule. So in this case, if you are doing reduction for this carbonyl group by using any, I have not given any reagent because there may be so many methods. It may be stereoselective, it may not be so. So but fine, after all, I am trying to say that by reduction we can change this C double bond O to CHOH. Okay. Now addition of alpha silyl carbanion to aldehyde or ketone. Now this is the most common, and most of the examples you will see for Peterson beta hydroxysilane formation. This is basically this last one. So addition of alpha silyl carbanion. So in presence of, that is, if it is already Grignard reagent, so you know there is a carbanion type of character, and if you have some electron withdrawing group here present, then in presence of base, this hydrogen will be very acidic, and we can generate negative charge. So it may be Grignard reagent, or you can generate it in presence of some base, but remember there should be an electron withdrawing group. Now this negative charge, it can attack at this carbonyl, it may be aldehyde or it may be ketone. So it may be R or H, because I have mentioned both. In this case H is present, and in this case we have H and R. Here it is H and MgCl, here it is H2 and R. So that is both possibilities are there. So in this way also we can make beta hydroxysilane. So these are the some of the methods, some of which may be stereoselective. Now very interesting point. Suppose we are doing direct olefination. What I am trying to say by direct olefination, and also the stereochemistry for this direct olefination. Here nucleophilic addition of silyl carbanion, to the C double bond O, and plus spontaneous elimination. So what we will do, we will not use any externally any acid or basic condition. It will be direct reaction. Okay, and see what is happening here for the stereochemistry. So suppose we have taken this R2CHO, this is the aldehyde, and in presence of and this is our another starting material. Now if it is magnesium, there will be formation of MgBr. If it is NBuLi, that is also another type of reagent possibility is there. And what is happening, the main important point is there will be some negative charge, and that will attack this carbonyl carbon. So this is the nucleophilic addition step, that is the first step. Now once it is happening, we will get diastereomeric adducts. Now among these two diastereomer, depending on what type of groups we have used, because here everything is in general. I have written R1, R2, R3, SI. So there may be all the possibilities are there. Now depending on the size of these groups, because we do not know what is R1, R2 or R group. R3 means total 3 R groups. It is not R3, total 3 R groups attached to silicon. So depending on these groups, whether these diastereomeric adducts, one of these will be major or whatever will be the result, that depends. But ultimately we will get these diastereomeric adducts. So these are the two possibilities. So see, these two are diastereomer, and the left hand side molecule, there is equivalent sign. You can draw it in this Newman projection, and for the right hand side diastereomer also you can do the same thing. Now this is the stable configuration, but suppose if you are bringing this negative charge over oxygen close to silicon, and if it is attacking here, so there will be a connection between Si and O. This is basically H complex, and there is a attachment of metal also, but for simplicity I have simply mentioned O minus. This negative charge when it is attacking this Si, and finally there will be removal of R3 Si and O, and you will be getting CC double bond. Now what are the possibilities depending on the size? Suppose the left hand side configuration is preferred. Why? Because here R3 Si is small. Now when R3 Si is small, that means this R group is very small. Now suppose we have Me3 Si. R3 Si, when it is Me3 Si, then you can apply this condition, it is very small, and here main focus is on R1 group and R2 group. They should be far from each other. So when they are far from each other, this is the stable way to draw the molecule, and in that case you will be getting E, because when you are bringing close to it, R2 will be close to H, R1 will be close to this H, so ultimately you are getting this E alkene. And the other side, right hand side is preferred if R3 Si is very bulky. So in that case you have to creep this group as far as possible from R2, and now R1 is bringing, we are bringing close to R2, and when this will attack here, ultimately OSI bond will be broken. You can say that this mechanism is quite similar to the mechanism that we have already seen for the base mediated. But remember, here we are not adding any external base. Whatever is happening, it is happening directly. It is one port. So this negative charge, it is attacking this Si, and ultimately these two groups, they are on the same side, and we are getting Z. So stereochemistry, here how we are controlling. For direct Peterson elimination, where external acidic or basic conditions we are not using, because this step is irreversible. The first step is irreversible, and the elimination is stereospecific. So these are the facts, and because of these facts, ultimately we can say that the stereochemistry of the first reaction, that is the nucleophilic addition, that is actually the all over stereochemistry controlling factor, that is for the overall process. So the configuration of the final products, configuration of the adducts, that is the diastereomeric adducts, that will be reflected here. So suppose if I am saying the ratio is X is to Y, then these two E and Z, that will also be the X is to X is to Y. So that is what is written here, that the configuration of the adducts, that will be reflected in the final EZ ratio of the olefinic product. So if we can somehow control this diastereomer adduct, that is this, suppose this is, we can make 8:1 or 9:1, then we can get these two as major, and that one of them will be major. Okay, so it will be either 9:1 or 1:9 like that, then it will be useful. So this is the another way to represent it, where everything is happening. There is a direct Peterson, not interrupted Peterson, and this is also you can say one port. Now some important features we will talk about this olefination reaction. You can say this is the silicon variant of Wittig reaction, where both the addition of alpha silyl carbanion to carbonyl compound and also the subsequent elimination you are considering together. So why I am saying so? Suppose if you look at this, here everything is happening together. That is the negative charge that is attacking here. You are getting beta hydroxysilane. Then depending on acidic or basic condition, or if you are not using any acidic condition or basic condition, it is some as the previous slide example, if it is directly some stereoselective formation of this, then also we can get one of the E or Z as major. But that is not the focus here. The focus here is when you are considering both the steps together. Suppose you are moving from this and you are reaching up to this point. So if you are focusing these 2 points, then obviously we can say, from the color also you can understand, the final alkene product, one side is coming from the aldehyde or ketone, and the other side, just focus on the color, other side is coming from this alpha silyl carbanon. So it is just like Wittig reaction. There also we use some carbonyl compound, and though there is no silicon use, there is phosphorus, right? But this is similar type, so that is why we can say this is a silicon variant of Wittig, and that is the reason it is also called Sila-Wittig. Okay. When Me3Si derivatives are used, suppose the silicon compound as a reaction partner you are using this R3Si group, that is Me3Si, then the byproduct will be like this, because ultimately from the medium there is removal of OH and there is removal of Me3Si. Now these 2 molecules together, it can make it, just like from alcohol as we get ether, same type of thing. So this will be the byproduct, and this byproduct is very volatile. Its boiling point is around 100. So it can be removed very easily. But in case of Wittig, you have to remove this type of side product, which is very difficult. Okay. So from that point of view, we can say this is advantage over Wittig, where we can remove this byproduct very easily. Next feature, the method is, this is number 1, this is number 2 feature, this is number 3. The method is especially valuable for the preparation of terminal or exocyclic double bond. So suppose you have some cyclic structure and there is exocyclic double bond, and it is also good method for methylation of hindered ketones. So suppose we have some hindered ketones, any R group, and we want to do methylation. That means we want to convert it to CH2 in place of CO. Then this method, it will be very good, because this part it will be coming from the SiMe3 and Cl. Now this is commercially available. So that is the reason we can use this method very easily, because when you are trying to make exocyclic double bond, this CH2 group, that will come from this part. So, and also this hindered methylation of hindered ketone, this group will be coming from this molecule, and this is commercially available. Basically MgCl, that is commercially available. So directly you can get this Grignard reagent, you don't have to make it, and directly you can easily make this type of exocyclic double bond or methylation of hindered ketones. This elimination is stereospecific. Why? Because depending on what type of diastereomer you have taken, suppose diastereomer 1, diastereomer 2, or you can write syn or anti. Now under the same condition, if one is giving you Z, another one, same condition, if one is giving Z, another one is will be giving E, or it may be if the first one is giving E, it will be giving Z. So that means this is stereospecific. This is an important feature, and its formation is regioselective. Now this is just like Julia olefination. Please watch the Julia olefination. You can get the link right here, right now, top right corner. Also I will mention it in the description box. So why it is regioselective, just like Julia olefination? So it is regioselective because this SiMe3 group and OH will be removed ultimately. And see, there are so many hydrogens also which is present at alpha position with respect to OH, but they will not be removed. Only SiMe3 and OH will be removed. So you can consider it as if it is equivalent to some proton, and proton is removed by the in presence of base. Similarly, SiMe3 group or any SiR3 group, that can be easily removed by some hard nucleophile. So H is replaced by some base, and this is equivalent to H, but now instead of base you will use some hard nucleophile. But whatever it is, ultimately these two groups will be removed. So you will always get CC double bond at this position where originally SiMe3 and OH present. So that is why it is regioselective, just like Julia olefination, where a sulfur compound is present. Okay. The use of organomagnesium compound. Now this is very helpful if you want to trap the beta hydroxysilane. Now why it is so? Suppose your purpose is to make beta hydroxysilane first, you don't want to do one port. then you can use this organomagnesium compound. The reason is Mg strongly binds with oxygen. That means this bond, it is stable. So the further elimination step, it becomes difficult. It will not happen. It will be, you can trap it, you can isolate it. So this is the important point. If you want to make a separate beta hydroxysilane, you can use this method. So that is all about, that is the first introductory idea of Peterson olefination. We have seen its mechanism and some important features, and I will discuss some important examples, synthetic applications in the next video. Thank you for your time.